Hello and welcome back to Bedroom Physics. This is part 2 of the vectors concept video. Today I'm going to be talking about unit vectors and I'm going to be talking about vector products. But first, let's start with unit vectors. So what is a unit vector? A unit vector is a vector with a magnitude of 1. It doesn't have any units, it's just one unit. It's not 1 meters, it's not 1 foot, it's not 1 centimeter, it's just 1 unit. And the sole purpose of a unit vector is to point into a direction in space. The way that we note unit vectors are the letter or the symbol that you choose for the vector with a little hat on top which looks like the tip of an arrow. The three most common unit vectors are I hat, J hat, and K hat. And as you can see here, I hat points in 1 unit to the x direction, J hat points 1 unit to the y direction, and K hat points 1 unit in the z direction. I think the best way to exemplify how unit vectors work is if we look at a unit circle and we take the radius to be vectors. So I have one here. There's a lot going on here, but I'm going to break it down step by step. So the first thing to notice is that I have my 2 unit vectors. Since this is a 2-dimensional graph, I have my unit vector I, which is 1 unit in the x direction, and my unit vector j, which is 1 unit in the y direction. I also have a unit vector u, and it's 45 degrees from the x-axis, and its magnitude is still 1 unit. Now, we also have vectors u of x times I hat and u of y times j hat. Now, since the unit vectors are being amplified, they're no longer unit vectors, right? So these have a value, and now these vectors have a magnitude of u of x and u of y. So the magnitude of u hat are the components in a root, squared, and summed, or just using Pythagorean theorem. However, if we remember from vector addition, in order to get a vector, we could also add 2 different vectors together, right? And we have here 2 different vectors. We have vectors u of x, I hat, and u of y, j hat. And they're the same magnitude as the components of u of x and u of y, and they go in specific directions, right? So let's extract some of the information here and kind of clear it up. So I have my vector u of x times I hat, and it's only going in the x direction and it has a magnitude of u of x. I have my vector u of y times j hat, it's only going in the y direction and has a magnitude of u of y. And I have my unit vector u hat. But wait a second, this looks familiar. This looks like a vector addition problem. Remember when we had displacement? We were going from point 1 to point 2, and if there's 2 ways to get there, if we go along this vector and this vector, we could also go along this vector, so they must be equal to each other, right? Exactly. So u hat is equal to u of x, I hat, plus u of y, j hat. And in this case, u of x and u of y is equal to square root 2 over 2. And the reason that is when we're looking at a unit circle and we're at either 45 degrees from the x-axis or 225 degrees from the x-axis, the components in the x and y direction will be the same in order for the magnitude of the radius or the magnitude of vector u hat to be 1. Okay, but wait a second. Vector u hat has a magnitude of 1, but we're adding 2 different vectors that don't have a magnitude of 1, and we're getting a vector that has a magnitude of 1. Well, how does that work? Well, remember that in order to find the magnitude of u hat, we have to do the root of u of x squared plus u of y squared. But the components of u are the same distances and directions of u of x times I hat and u of y times j hat. So couldn't we find the magnitude the same way as we did before, simply by rooting the components squared and added? And the answer is yes. So we have the magnitude of u hat is equal to the square root of square root 2 over 2 squared plus square root 2 over 2 squared, which is 2/4 plus 2/4 on their square root, which is equal to 1. So now we know we can note vectors by adding other vectors. I mean, this is an old thing, right? But we never thought about it in this way. So now that we know that, we can add vectors together using this kind of notation. And here I have an example. So I have vectors v and vectors q being added together. Note they are not unit vectors, they don't have the hat on top, it's just an arrow, okay? And the combination of the two is equal to v of x times I hat plus v of y times j hat plus v of z times k hat plus q of x times I hat plus q of y times j hat plus q of z times k hat. But wait, since we add vectors adding the components, and the components are the same distances as each one of these vectors, couldn't we just add them up normally? And the answer is yes, we can. So instead of having this big mess, we could just organize it like this. We can do v of x plus q of x times I hat plus v of y plus q of y times j hat plus v of z plus q of z times k hat. Now this creates an entirely new vector r, that I've created. I mean, you can name it anything you want. But I've noted that vector r is equal to r of x times I hat, which is the same thing as v of x plus q of x times I hat, plus r of y times j hat, which is the same thing as the term here, and r of z times k hat, which is the same thing as this term. And here is a graphical description of what's happening. So we have vectors v, we have vector q, and we have vector r. Vector r is the addition of vector v and q. Here are my unit vectors, and here are my vectors that describe vector r of x times I hat, r of y times j hat. So vector r is not a unit vector. The magnitude of vector r is equal to a meters. But say I don't want to travel the distance of vector r. Say that I only want to travel in the direction of vector r. Okay? How do we do this? We can make vector r into a unit vector. I'm going to explain why this works in the next part, but this is how we do it. Vector r over the magnitude of vector r. While we talk about the next part, think about it if you want, don't think about it if you don't want, I'll explain it, but this is pretty interesting. Okay, so now let's talk about dot products. I thought I was going to be able to get to cross products today as well, but it's looking like if I talk about both dot products and cross products, the video is going to be too long. So I'm only going to talk about dot products, and then I'm going to make a third video talking about vector products, and that's actually probably when I'll talk about why we can make vector r into vector r hat. But now let's talk about dot products. So in order to do a dot product, you have to have two vectors where the tails are touching. Now, I mean, the vectors can be anywhere on the graph, but in order to do it, you kind of have to touch tails because you need to find out the angle between them. The dot product is defined, in this case, as the magnitude of vector v times the component of r in the v direction. Alternatively, we could define the dot product between r and v as the magnitude of r times the component of v in the r direction. When we note dot products, we put a big dot in between the vectors, so vector v dot vector r, and the dot product is equal to the magnitude of both vectors multiplied times cosine theta, and the theta is the angle between them. But most importantly, the dot product of a vector, of two vectors, is equal to the x components of each vector multiplied plus the y components of the vectors multiplied plus the z components of the vectors multiplied. Now, we won't be using this right here in this part, but I think it's important to know that another way to note vectors when you're not using the unit vectors is if you have a vector f, it's also equal to the point little bracket f of x comma f of y comma f of z. This is just another way to note a vector. And before we do the entire dot product of r and v, let's just do the dot products of each individual unit vector. So here I have a list, so I have I hat dot I hat, and it is equal to j hat dot j hat, and it's equal to k hat dot k hat. Why? Well, both the magnitudes are 1, and the angle between each one of these vectors is 0. So cosine of 0 degrees is 1, 1 times 1 times 1 is 1. But when you change it up, and you do I hat dot j hat, which is equal to I hat dot k hat, which is equal to j hat dot k hat, well, the angle between each one of them is 90 degrees. So you're going to have both the magnitudes, which is 1, but then you have cosine of 90 degrees, and we all know that cosine of 90 degrees is 0. Now that we know this, it's going to make our life much easier when we do the dot product, but let's get started. It is kind of hefty. So the dot product of vectors r and v is going to be equal to r of x I hat plus r of y j hat plus r of z k hat dot v of x I hat plus v of y j hat plus v of z k hat. Now the way that we multiply this is we're going to FOIL it out, so we have to do the first term, multiply the first term here, and the same first term by the second term, same first term by the third term. You know how it goes. And what we're going to get as a result is we're going to get r of x I hat dot v of x I hat plus r of x I hat dot v of y j hat plus r of x I hat dot v of z k hat plus r of y j hat dot v of x I hat plus r of y j hat dot v of y j hat plus r of y j hat dot v of z k hat plus r of z k hat dot v of x I hat plus r of z k hat dot v of y j hat plus r of z k hat dot v of z k hat. But wait, if the vectors are not going in the same direction, don't they necessarily have to be 0, since the degree between them is 90 and cosine of 90 degrees is 0? Yes, they do. So what happens is all the ones which the vectors are not being multiplied by a vector that is going in the same direction, they're all going to go to 0. So we keep this one goes to 0, this one goes to 0, j and I, 0, j and j is fine, j and k, 0, k and I, 0, k and j, 0, r of k and k, we're good there. So did I get everything? Looks like it. So the new total is going to be r of x I hat dot v of x I hat plus r of y j hat dot v of y j hat plus r of z k hat dot v of z k hat. But we know that the dot product is also both the absolute values and cosine theta, where theta is the angle between them. Well, the angle between I and I is 0, so cosine goes to 1. So we are just left with the magnitudes, but since the magnitudes are the value of them themselves, so in the end it'll just be r of x times v of x plus r of y times v of y plus r of z times v of z. And that right there is how you do the dot product. In the next video, I will talk about how to do the cross product. Thanks for watching, and I hope to see you on the next part.